Welcome to our next lesson. Today we're going to be looking at resisted horizontal motion. So straight into it. When we've got an object that's moving through some medium, it could be air or water, there's going to be some sort of resistance force of that particular medium that it's traveling through, which is going to slow down that object's motion. So obviously it's going to be acting in an opposite direction to the motion because it's acting as a resistance. So the higher the velocity of that object, the greater the resistance is going to be. All right, it's in direct relationship to how fast it is traveling this particular resistance. So for horizontal motion, we're assuming we're moving fast enough that there are no other forces that are going to be apart from that resistance due to our velocity or the velocity squared, and that will depend on the speed, and we'll look at that in just a second. So the first one is linear resistance. All right, so this is where it's directly proportional to the velocity. So this is when objects are usually moving on the slower side, and then that resistance is due to some sort of viscosity of the medium. So for example, if we are traveling through something sticky, that's going to slow down the velocity. So for example, we've got the picture there of the car driving through mud. If you've ever tried to walk through mud or drive through mud, you will know that that substance is quite thick and that it slows you down, and there's kind of a suction that's happening there. Right? We just assume that there's just going to be some sort of resistance that is occurring overall, which is acting in the opposite direction to the motion of the particular vehicle. Mathematically, we write that resistance as the negative K times V, and K is just some constant. Right? There's going to be some sort of resistance constant, that is K, and V is going to be our velocity. It's negative because it's acting against the motion of the object. Now we know that for any particular force, it's just going to be mass times acceleration. So then the mass times acceleration is going to be the negative constant times velocity. So we can rearrange that and say that our acceleration is going to be the negative of our constant of resistance over mass multiplied by the velocity. So that's linear resistance. That's where it's directly proportional to the velocity. The other option is quadratic resistance. So this is where we're traveling at higher speeds, and then there's a drag related to the momentum transfer between our object that is moving and the fluid in which it is traveling. Now that fluid can still be air, it doesn't have to be an actual liquid. In this instance, it's when it's in direct relationship to the velocity squared. So our resistance now is equal to negative K times the velocity squared. Again, that K is just our constant of resistance. So again, mass times acceleration is going to be our negative K times V squared. So that acceleration now is the negative K over mass times the velocity squared. All right, so if it's relatively slow, it will be the linear resistance. If it's traveling relatively fast, it will be our quadratic resistance. Usually you'll be given either that it's in, it'll tell you what sort of resistance it is, or if it's in direct relationship to the velocity, or if it's in direct relationship to the velocity squared. That information is usually given to you, so you don't have to try and figure out which one is which. So there are a couple of formulas for acceleration. So if we are looking for displacement in terms of t or velocity in terms of t, then our acceleration is going to be dv over dt. However, if we are looking for velocity in terms of displacement, then the acceleration is going to be equal to the velocity times dv dx. So both of those are, well, the first one should be pretty straightforward. You've seen that before, but the second one is probably relatively new. All right, the velocity multiplied by dv dx will give us the acceleration. All right, let's look at an example. So example 1, a particle of mass m, initially with a speed of v0, moves horizontally against a resistance proportional to the square of its speed. All right, so straight away we've been told this is the square of the speed. So we can write down in there that mass times acceleration equals negative kv squared. We want to express its velocity in terms of the distance traveled and then its displacement in terms of velocity. So let's start out by doing the velocity in terms of the distance traveled. So we want to have it in terms of x, v in terms of x. So this is where we want to substitute in something for acceleration. So we need to get acceleration on its own first. So we divide everything by m. We get that acceleration is negative k on mv squared. And the previous slide, we had that for when we want to find velocity in terms of x, acceleration is just v times dv dx. So now I've got v's on both sides. What I'm going to do is divide both sides by v squared. This way I get all my v's on one side. So dividing both sides by v squared, we're going to have 1 over v dv on dx is equal to negative k on m. So I want to get rid of that dx on the left. So I'm going to basically multiply both sides by dx so that it cancels out on the left, and I'm going to have a dx on the right. But that means we're going to be taking the integral of both sides. So we've got the integral of 1 on v dv. Well, hopefully we recognize that that's just going to give us the natural log of v. And then negative km times the integral of dx. Well, the integral of dx is basically 1 dx. So the integral of that is x. And then we've got ourselves, don't forget, a constant of integration. Now we could put a constant of integration on both sides. So we'd have like plus c on one side and plus d on the other. We then take c away from both sides. We're going to have d minus c on the right, and then d minus c is just basically another constant. Let's call it e. We can do that, but ultimately that's just extra steps. We know there's going to be some constant in the long run. So that's what we've done there. So we need to work out what our constant c is going to be. So what information have we got? Well, we've got initially we had speed of v0. So v0 means that we are starting at x is 0 when t is 0. Not like t is relevant, but that's what that basically is telling us. So when x is 0, v is equal to v0. So if we were to substitute that in, we're going to have the natural log of v equals 0 plus c. So therefore c must be the natural log of v0. So then I can write that in. So the natural log of v is equal to k on mx plus the natural log of v0. So let's bring all of our terms of v onto one side. So then we've got the natural log of v minus the natural log of v0 is equal to negative k on mx. Log laws. If I've got log of something minus the log of something else, that means I can just do a division. So that can be simplified to the natural log of v on v0 is equal to negative k on m lots of x. Now I've called this equation 1 because we're going to be using this equation a couple of times. So the first thing is we want to know, well, what is its velocity in terms of distance traveled? So what we're going to need to do is get v by itself. So if I raise everything to the power of e, the natural log goes away on the left. And we've got that v over v0 is equal to e to the negative k on m lots of x. Multiply both sides by v0, and we get that the velocity is going to be the initial velocity times e to the power of negative k on mx. So that's our first part there. We've got velocity in terms of the distance traveled. And now we want displacement in terms of velocity. Well, this is where we go back to equation 1. Its displacement there, x, we want that in terms of velocity v. So what I'm going to need to do is just divide both sides by k on m. So if I'm dividing by negative k on m, I'm multiplying by its reciprocal, negative m on k. So therefore, our displacement is going to be negative m on k times the natural log of v over v0. All right, example 2. A particle of mass of 3 kilograms is propelled from the origin along the x-axis with an initial velocity of u meters per second. The only forces acting on the particle in the x direction are friction, which is going to be a constant 18 newtons, and a drag due to air resistance, which is going to be v squared newtons, where v is the velocity of the particle t seconds after leaving the origin. We want to show dv dt is equal to negative 6 minus a third of v squared. So the first thing we've got there is the force that is propelling it along. So we know that force is going to be mass times acceleration. Now its mass is 3, but we don't know what the acceleration is, so we will just leave that as a. The other force that is acting on this particular thing is acting in the opposite direction. So we've got friction and air resistance acting against it. So we've got 18 newtons of friction and then V squared newtons of air resistance. So we want to add those together, but it's acting in the opposite direction to that motion. So it's going to be in a negative direction. Now we wanted to show that dV dt equals -6 minus 1/3 of V squared. So we can make those two particular things now equal. All right, dV dt is going to be our acceleration. Well, we know that 3 lots of that acceleration is equal to -18 minus V squared. So I'm just going to divide everything by 3, and we get that A is equal to -6 minus 1/3 of V squared. Like I said, A is dV dt. So therefore dV dt equals -6 minus 1/3 V squared, as required. Okay, so for part B, we want to show that T equals 1 on root 2 lots of the inverse tan of 3 root 2 lots of U minus V, all over 18 plus UV. So from part A, we know that dV dt is equal to -6 minus 1/3 of V squared, and that's the same as saying 3 lots of dV dt equals -18 minus V squared. Doesn't matter which one of those we want to use, we'll still get to the next step the same way. So if I'm doing the one on the left, I'm going to pull out a factor of -1/3. If I'm doing the one on the right, I'm going to multiply by 1/3. Either way, what I'm going to get is that dV dt is equal to -1/3 multiplied by 18 plus V squared. Now the joy of that is I can switch out my 18 plus V squared with dt on the other side. So I'm just going to switch those two around. So now we've got dV over 18 plus V squared is equal to -1/3 of dt. So I've got all my V's on one side and all my T's on the other. So what that means is I'm going to need to take the integral of both sides. Now, because we've got an initial velocity of u and an overall velocity of v, we need to take the definite integral between u and v. And then on the right-hand side, we've got -1/3 times the integral of 1 dt. Well, 1 dt, the integral of that is just going to be t. On the left-hand side, hopefully we can look at that and realize that that's going to be inverse tan. So what we're going to get is 1 on root 18, lots of the inverse tan of v on root 18 minus the inverse tan of u on root 18. All right, that's putting in our definite integral values. And that's going to be equal to -1/3 of t. Don't need to worry about a constant of integration because we've got definite integrals. Okay, so that 1 on root 18 out the front is messy, so let's multiply both sides by root 18. Now, root 18 is also just root 9 times root 2, so that's 3 root 2. So if I do 3 root 2 divided by 3, on the right-hand side, I'm going to have just -√2. All right, so I've got a negative on the right-hand side. Let's get rid of the negative. If I multiply everything by a negative, on the left, I'm going to have negative inverse tan of v on 3 root 2 plus the inverse tan of u on 3 root 2. So I'm going to switch those two around so that I've got u on 3 root 2 minus v on 3 root 2. All right, so I've got these inverse tans there. I need to get rid of those. How can I get rid of those? Well, I can just take the tan of both sides because the tan of the inverse tan, they cancel each other out. So let's take the tan of both sides. And what we've got now is that the tan of root 2 lots of t is equal to the tan of inverse tan of u on 3 root 2 minus the inverse tan of v on 3 on root 2. So let's just clear all of that out. And so we're just left with that there. Now, what we've really got here is the tan of something minus something else. We can't just cancel the tan and the inverse tans out straight away. What we really have is tan of A minus B. So we're going to use that rule of tan of A minus B to expand that out. So A is going to be the first part of our bracket there, so the inverse tan of U over 3 root 2, and B is going to be the second part, the inverse tan of V on 3 root 2. So now I can substitute those into that expanded form, and we're going to have the tan of the inverse tan of u on 3 root 2. Well, that's going to cancel out, and we're just going to be left with u on 3 root 2. And then the tan of the inverse tan of v on 3 root 2. The tan and the inverse tans will cancel out. We're just left with v on 3 root 2. Likewise on the bottom, tan A times tan B will just mean that the tans and the inverse tans cancel out, and we're going to be left with u on 3 root 2 times v on 3 root 2. Let's simplify that down a little bit. So we're going to have u minus v on 3 root 2 as our denominator, and 1 plus uv on 3 root 2 squared as our denominator. Now I've intentionally left it as 3 root 2 squared, and that'll become clear in a second. Because what I want to do is I want to get rid of 3 on root 2, certainly off the numerator if nothing else. So what we're going to do is we're going to multiply by 3 on root 2 over 3 on root 2. Reason for that is my 3 on root 2 will cancel out with the 3 on root 2 on the bottom of our numerator. And then on our denominator, we're going to have 1 times 3 root 2. But then we're going to have 3 root 2 cancel out with one of those 3 on root 2's squared. So we're going to be left with u minus v all over 3 root 2 plus uv on 3 root 2. We still got 3 root 2's there, so basically what we want to do is we want to rationalize that denominator now. We're going to multiply both again by 3 root 2 on 3 root 2. So on the top, we're going to have 3 root 2 lots of u minus v. And we're going to have 3 root 2 times 3 root 2. And then we're going to have uv, because those other 3 root 2's are going to cancel each other out. 3 root 2 times 3 root 2 is 9 times 2, so that's going to give us 18. Again, let's just clear all of that out and just simplify it down. So what we've got there is tan of root 2 lots of t is equal to 3 root 2 lots of u minus v all over 18 plus uv. So we want to get t on its own, so we're going to take the inverse tan of both sides. And then we've got root 2 lots of t on the left there, so we want to divide both sides by root 2 or multiply by 1 on root 2. So that cancels out on the left-hand side, and on the right we've got now 1 on root 2 times the inverse tan of 3 root 2 u minus v over 18 plus uv, which is what we wanted, so we have completed that as required. And now for part C. By using that dv dt is equal to v times dv dx, we want to find an expression for v in terms of x. So going back to part A, what we've got is that dv was equal to negative 6 minus a third of v squared. So we're going to have that equal to v times dv dx. So what we've got there are v's on both sides of that equal sign. We want v equal to something in terms of x. So let's put all of our v's on the left and our x's on the right. So we can just switch out everything on the right-hand side with our dx on the left. And what we're going to have is v over negative 6 minus a third v squared dv is equal to dx. Now I don't like that negative third there, so let's multiply everything by negative a third. That way it gets rid of not only that third, but it also will get rid of our negative. So what that's going to give us is v over 18 plus v squared dv is equal to negative 1/3 dx. All right, so we're going to need to take some integrals there. Now on the left-hand side, the top is not quite the derivative of the bottom. If we had 2v on the top, well then it would just be the natural log of 18 plus v squared. But because we've only got v on the top, we've only got half of that natural log. So on the left-hand side, we're going to have half of the natural log of 18 plus v squared. Negative third integral of dx is just going to be x. And of course, we've got a constant of integration. So to get rid of that half, let's multiply both sides by 2. And now we've got the natural log of 18 plus v squared is equal to negative 2/3 of x plus d. All right, because we've got twice the constant c, so we're just calling it another constant d. Remember, the letter isn't overly important. Now we want to get rid of the natural log on the left-hand side. The way we do that is we're going to raise both sides to the power of e. So the e and the natural log cancel out on the left-hand side. We're just going to be left with 18 plus v squared, and that's equal to e to the negative 2/3 of x plus d. Now remember, when we've got a plus as a power, what that really means is that we're multiplying an equal base with that power. So we can expand the right-hand side out to be the same as e to the negative 2/3 of x times e to the power of d, right? That's just our index laws. So we want to find some value for e to the power of d. Well, what do we know? We know that when x is 0, right? This is where our displacement is 0. What is actually occurring? Well, our velocity is equal to u, our initial velocity. So we can substitute in x is 0 and v is equal to u. Then what we get is 18 plus u squared is equal to e to the power of 0, so 1 times ed. So there's our value for ed. It is 18 plus u squared. So we can now substitute that back in to the previous line. So now we've got 18 plus v squared is equal to 18 plus u squared times e to the negative 2/3 of x. Well, if I take 18 away from both sides, I'm now left with v squared is equal to 18 plus u squared, all multiplied by e to the negative 2/3 of x minus 18. So there's my expression for velocity in terms of x. We don't need to get it down to a single v. We can have v squared. That's totally acceptable because that is an expression for our velocity. And that brings us to the end of this exercise. So if you want to go on to exercise 705 on page 291, like I said before, most of the questions in there should stipulate whether or not it's a relationship in terms of the velocity or in relationship to the velocity squared. As always, any questions, feel free to let me know. Email or message via Google Classroom, of course, are the best ways to do that. Latest news is that lockdown is going to be extended, so I can't see us coming out of this anytime soon. So I will continue to be putting these lessons up on Google Classroom. If you have any questions, yes, please let me know. Otherwise, I will talk to you soon.